Let's talk about homework set number 33. We're getting towards the end of the semester here. This homework set is all about static equilibrium. And in static equilibrium, we have two basic ideas. One is that if there's no linear acceleration, then the net force has to be zero. And if there's no angular acceleration, then the net torque has to be zero. In this case, if your center of mass is not accelerating, that means all the forces have to add up to zero. All the left force balances all the right force, all the upward force balances all the downward force. If something has no angular acceleration, if it's either not rotating or rotating at a constant angular speed, then the net torque is zero. That means all the torque that's trying to make it go clockwise is balanced by all the torque that's trying to make it go counterclockwise. Okay, and those two ideas are what allow us to solve a huge collection of problems, and indeed this makes up the whole static equilibrium course that the architecture majors have to take. It's one of the more challenging courses that they take. Let's look at problem 24 in chapter 9. In this case, we got Bob and Will. Okay. They're brothers, and you'll find throughout these problems that Bob always ends up with the lion's share of the work. Will's kind of on the lazy side, and so they're holding up this beam, and the mass of the beam is 71 kilograms, and it's 2 meters long. Okay, and Will is pushing right at the end, and Bob is pushing a distance 0.6 meters from the end. And they've decided to use this beam, for whatever reason, to carry their lunchbox, which has a weight of 200 newtons down the road. Okay, it seems like a difficult way to carry your lunch, but there it is. And we want to know how hard is Will pushing and how hard is Bob pushing. Now your gut tells you that Bob's pushing harder than Will. He just seems to be taking a more difficult approach to this. We're looking for forces, and we're looking for forces on the beam. And so that means we should draw a free body diagram for that beam, that big old piece of lumber. Okay? But not just any free body diagram, since we're going to be worried about the torques, and the torques depend on where the forces are applied. We're going to be drawing an extended free body diagram. Okay, an extended free body diagram is a picture of the beam with all the forces that act on the beam put on that picture in the place where they are applied. Now, the first force we put on any free body diagram is the gravitational force, or weight force. And as we discussed in class, we can always put that force at the center of mass, okay? And that center of mass is going to be right in the middle of the beam. Now we know that that's just going to be the mass of that beam, 71 kilograms, times G, 9.8, we'll call it 10. So that's going to give me 710 newtons. I then ask, are there any magnets in this problem? No, not at all. So what touches the beam? Well, I've got this string pulling with a tension force on the beam, and that's going to be equal to the weight of this lunchbox, which is 200 newtons. I know that because I could also draw a free body diagram for the lunch box. That'd be the weight down and then be the tension and the string up. This is the other end of that same string. Okay, we know that the tension at two ends of a massless string are always the same. The only other things that touch this beam are Will, that puts a normal force here, and Bob, which puts a normal force here. Okay? Now, that's our free body diagram. Those are all the forces that act on that beam. And I know that all of the upward force has to balance all of the downward force by this principle here. So I know that the normal by Will on the beam plus the normal by Bob on the beam has to equal the total downward force of 710 newtons plus 200 newtons, okay? Or 910 newtons. But that's two unknowns with only one equation. That's not going to do it for me, okay? I can't solve for either of those unknowns. So what I have to do is balance the clockwise torque with the counterclockwise torque. Now, let's see if I can find a better pen here. Before we can balance clockwise and counterclockwise torque, we have to pick a pivot point. Now, in some problems, there just seems to be a natural pivot point because there's an axis of rotation. But that's not how we choose our pivot point in equilibrium problems, static equilibrium problems. Because in a static equilibrium problem, typically things aren't rotating about any point. And so that means we can choose any point whatsoever in the problem, and the torques will be balanced about that point. And so our choice of pivot becomes one of practicality. I have two unknowns here. I have this unknown force and this unknown force. And if I can eliminate one of those from my equation, it'll be much simpler to do the math. Now, since torque is a force times a distance from the pivot, that means there's two smart places to choose my pivot. I can choose my pivot here, in which case this force would be giving me no torque. It would drop right out of the torque equation. Or I could choose this to be my pivot, in which case this force would do no torque, and it would drop right out of the torque equation. Well, I'm going to choose this point right here to be my pivot. Again, just for convenience. Now, at this point, I have to decide which forces are doing clockwise torques and which are doing counterclockwise torques. So what I do is I use my imagination. I pretend that there's a great big golden spike going right through that pivot, that X right there, just pinning it to the sky and forcing this beam to rotate about that pivot as if it were a hinge. And then I ask for each of these forces, is that force trying to make that hinge go clockwise about that pivot or counterclockwise about that pivot? Well, like we said before, this force is acting right at the pivot. That's like going up to the hinge of a door and pushing at the hinge. Doesn't do anything for opening the door. Okay, that has zero torque. That's why I chose my pivot there. Now this force, this weight force, is trying to make it go clockwise. So I'm going to put it on the clockwise side of the equation here. And that's going to be 710 newtons times the distance 1 meter away from the pivot. Now this force by the string is also trying to make the beam go clockwise. And so I'm going to put it down on the clockwise side of the equal sign. So that'd be 200 newtons times its lever arm, which is the whole length of the beam, or 2 meters. Okay. The only force that's trying to make this go counterclockwise is the unknown force by Bob on the beam. Now, we were given this distance of 0.6 meters from the right end of the beam. That's where Bob is pushing. And folks, this is an old exam question, and that's one of the most common mistakes made on the exam, was that they put the lever arm as 0.6 meters, because that's the number that was given on the picture. But what we want is the distance to the pivot. What's important is that this is acting 1.4 meters away from the pivot. So I would multiply this by 1.4 meters. Now when I solve this for the normal force by Bob on the beam, I get 793 newtons. So I should draw this arrow longer. Okay, this is 793 newtons. Now again, if I go back here, I can now use Newton's second law, the linear law, to figure out how hard Will is pushing. Well, all the downward force is 910. All the upward force has to also be 910. And so that means that this normal force by Will is going to be 117 newtons. Because if you add 117 to 793, you get 910. Okay, that's a fairly decent problem, the type that you might expect on